Hi guys. So in the previous lecture we talked about conditional expectations. Today let's talk about properties of conditional expectations. So the first property I want to talk about is called linearity of conditional expectation. So what we're going to do is we have two, let's assume that we have two random variables x and y that depend on the first n coin tosses. Okay, what we want to do is we want to take expected value of a linear combination of x and y. So let's define a constant c1 and another constant c2. So you want to take expected value of a linear combination of this of these two random variables at time n, such that n is less than equal to time n. So these random variables basically depend on the first n coin tosses, and we want to take the expected value at time n. Okay, and what the linearity of conditional expectation says is that this is equal to c1, and we take the expected value of x plus c2, expected value at time n of random variable y. Okay. That basically is what the linearity of conditional expectation is. Now next what we want to talk about is taking out what's known. Now let's assume that we have another random variable x again, but instead of depending on the first n coin tosses, it depends only on the first n coin tosses. Okay, and y still depends on capital N coin tosses, and again 0 is less than n, less than equal to n, right? Now let's say we want to calculate expected value of x of y. So what taking out what's known basically says that you can take out from this expectation anything which is known at that point in time. So for example, we want to take the expectation at time n, and since this random variable x depends only on the first n coin tosses, at time n the value of this random variable is known. Okay, so we can take that out of this expected value. So this would become x. Okay, so we basically have taken out this value with this random variable x from the expectation because the value of x was known at time n, because x only depended on the first n coin tosses. This is called taking out what's known. Now let's assume that we have another time period m such that m is greater than n but less than capital N. Okay, now let's assume that we want to take expected value of x in this fashion. So what we want to do is, x is a random variable that depends on the first n coin tosses. Okay, what we want to do is we want to first estimate the value of x at time m, which is given by this expected value of random variable x at time n. And if you remember, we talked in the previous lecture that a conditional expectation of a random variable is also a random variable. Okay, so once we take this condition, when we take this expectation, what we get is still a random variable, and we can again take the expectation of that random variable at a previous time. So we are moving it, first we are taking the expectation here, then we are taking the expectation here. What this property says is this is simply equal to expectation at time n of that random variable. Okay, so instead of taking the expectation at m and then taking that expectation at time n, we can directly take the expectation at time n of that random variable. Okay, this is called iterated conditioning. Iterated conditioning. Okay. Now let's talk about independence. So fourth property is independence. So let's assume that the random variable x depends on n plus 1 to n coin tosses. So it doesn't depend on the first n coin tosses, okay? So it only depends on the n plus 1 to n coin tosses. Now let's assume that we want to take expected value of x at time n, okay? So what we want to do is we want to take expected value of x given the information available to us at time n, okay? But if random variable x doesn't depend on the first n coin tosses, then the information basically is really nothing, right? It doesn't really help us in estimating the value of x. So what this property basically says is, if x doesn't depend on the first n coin tosses, then it's simply equal to taking the expected value of x as if we had no information available, okay? This is called independence. Now, fifth one is Jensen's inequality. So let's assume that we have a convex function, okay, and what we want to do is we want to calculate expected value at time n of a convex function of x, where x is a random variable that depends on the first capital N coin tosses, okay? What Jensen inequality says is this is greater than equal to function of the expected value, okay? This is called Jensen's inequality. So these are the 5 properties I wanted to talk about of conditional expectations. You know, what we could do next is we could take one of these examples and apply it to, you know, our model that we were discussing in the previous lecture and see if this holds, okay? So what I've done here is I've basically written down the same stock process from our previous lecture. So basically what we're doing is we're starting with the stock at time 0 whose value is 4. Then every time we toss a head, the stock doubles up. Every time we toss the tail, the stock goes down by half. And we do that for three coin tosses, okay? So if we do that, this is basically the stock process. And what I would like to do is I would like to try to apply one of the properties that we discussed so far and see how it applies to this particular model. So what I want to do is I want to calculate expected value at time 1 of S2 plus S3. And according to our linearity of conditional expectation, this should be equal to S2 plus expected value at time 1 of S3, right? Now, how do we prove this? Let's just make sure you know, that we understand that at time 1 we basically are calculating. We are calculating expectation at time 1. Okay, expectation at time 1, we could be in either one of these two states, right? So we could have either tossed the head or a tail. So this basically is in effect two different equations. So what we need to prove is S2 plus S3. If the first coin toss was a head, then that would be equal to expected value of 1 at time 1 of head, expected value at time 1, S3 if it was a head. So this is the first equation if we were in this state, or we could be in the other state where we got a tail first, then this would become E1 of S2 if it was a tail plus E1 of S3 if it was a tail, right? So this equation basically comprises of these two states, right? We could either be here, we could be here, and in both these states we need to prove that this equation holds. And if this equation holds in both these states, then this equation holds, you know, then it's not dependent on the coin tosses, and basically this equation holds for all. That's how we're going to prove it. Now let's just, you know, calculate the first part here. The second part I'm going to leave that for you guys to do it yourself. Okay. So if you remember from in the last class when we were discussing conditional expectation, we've already calculated this. Okay, expected value of random variable S3 at time 1 if you got a head. Okay, we've already done the calculation in the previous class, and we know what the expectation was. It was 12.5. Okay, assuming probability of a head equals probability of a tail equals half, right? So what we should do is now we should just calculate this expectation of S2 at time 1 if it's a head. So we basically standing here, we want to calculate the expectation of S2. Okay, so what would this be? So expectation of S2 at time 1 if it was a head would simply be, so what we can only get two possible values of S2 from here, right? So if you're standing here, we can either be at 16 or a 4. If we toss a head, it will be at 16. If we toss a tail, it will be at 4. So we can just simply write this expectation as 16 times probability of getting a 16, which is half, plus 4 times probability of getting a 4, which is also half. So this becomes 10. Okay. So this is 12 and a half. This is equal to 10. So the sum of these two becomes 22.5, right? So right hand side basically has become 22.5. So now let's calculate the left hand side, which is S2 plus S3. So if we are standing here, we have two coin tosses remaining, right? We have already tossed the first coin and that was a head. Now we have two coin tosses remaining. In those two coin tosses, we can toss either a head-head, a head-tail, a tail-head, or a tail-tail. These are the only four possible outcomes, right? So let's figure out what is the value of S2 plus S3 in all of these four outcomes, okay? So if we toss two heads, we had already tossed the head, now we're tossing two more heads, so we would get this particular outcome, which is head in the first go and two more heads, the total 3 heads. The value of S3 in that case would be 32, right? So S2 plus S3 would be 32 plus, what is the value of S2 if this was the outcome? The value of S2 only depends on the first two outcomes. It doesn't really care about the third outcome. And the first two outcomes was head-head. So value of S2 would be 16. And what is the probability of getting two heads from this point? That is basically 1 by 4, right? So we were already here. We tossed the coin twice again. So we got this particular outcome, and getting two heads was 1 by 4. Similarly, we could have tossed, instead of two heads, we could have tossed a head and a tail. If it was a head and a tail, we were already at a head. And if we toss the head and a tail now, we were already at a head. So the total outcome would have been, we were head, head, tail, right? So what is the value of S3 at head, head, tail? It's 8. So we write 8 plus, what is the value of S2 if it was head, head, tail? Well, S2 only depends on the first two coin tosses. So this is same as S2 of head, head. S2 of head, head is 16. Multiplied by probability of getting a head, tail. Okay, because we were already at a head, so we tossed two coins and we need to figure out what is the probability of a head, tail, which is 1 by 4. Plus, we could have now, instead of tossing a head, tail, we could have tossed a tail, head. So in that case, what would have the outcome become? The first was already a head. Now we could have tossed a tail and a head. This would be, so what is the value of S3 in this situation? Head, tail, head, head, tail, head, S3 would be 8. Plus, what would be the value of S2 if it was a head, tail, head? Again, the first two outcomes was head, tail. So value of S2 in a head, tail is 4. So this is 4 times, what is the probability of getting a tail head? 1 by 4, right? Plus, lastly, if we could have also tossed two tails then. So then what would have the outcome become? The first was a head because we were standing there. Now we could have tossed two tails. So head, tail, tail. S3 of head, tail, tail is 2. Plus, what is the value of S2 in this particular outcome? S2, as we have said, only depends on the first two head, tail. S2 of head, tail is 4. So this becomes, and probability of getting a tail, tail is again 1 by 4. Okay. So this you can see is equal to 12 plus 6 plus 3 plus 1.5 equals 22.5. Okay. So here you can see the right hand side was 22.5, the left hand side is also 22.5, so this first equation is basically satisfied. Now we can similarly do it for equation number 2. Make sure that the right hand side is equal to the left hand side. I'm not going to do that. I'm going to leave it to you guys to basically give it a try. Okay, and you'll see that obviously the left hand side and the right hand side would be equal. Hence this equation holds, and we basically have just checked the linearity of conditional expectations. Now what we can do is, we can also apply the same concepts to taking out what's known, iterated conditioning and independence, and we can make sure that we understand how this mathematics works. I'm not going to do that here, but if you guys are interested, Steve Shreve's volume 1 has given examples of applying all of those properties to this particular model. You can check it out there, but what I suggest is you basically try to do it yourself. Okay, you try to do it yourself, you'll actually learn more, you'll understand this concept a lot better. So that's pretty much all I wanted to discuss here about conditional expectation and its properties. In the next class, we're going to talk about martingales. Okay, so I'll see you then. Bye.